Hello, my wonderful students. How are you people today? Hope you are fine and safe. You are welcome to another physics class with your teacher, Asaga Prince Chinebomba. This is a class for our SS2 and SS3. Last time we tried as much as possible in our physics class to discuss the mirror formula and the linear magnification of image formed by spherical mirrors. We also talked about refraction of light waves. We learned that refraction is the bending of light rays when the ray travels from one medium to another due to the difference in the velocity of the light ray in the different media. That is the bending of light as the ray travels from one medium to other as a result of the difference in densities of the two media and also the difference in velocity of the light that actually determines, as the light moves from one medium to other, the velocity or the speed of the ray actually determines the extent to which this particular ray is going to bend or diffract. We also learned the different ways in which refraction can occur in life. We learned the different ways, like when we now place a straight rod inside a bowl containing water, that it will appear to be bent. That is our natural phenomenon of refraction. We also said when we use our rectangular glass prism or the glass block and place on top of a written alphabet or written alphabets, that there will be a portion where that particular slab is being placed, the letters there will appear to be raised with respect to the other ones. These are what we discussed last time. So today we are going to go along to talk about refraction again, but this time refraction through rectangular glass prisms. Refraction through rectangular glass prism. Refraction through rectangular glass prism. Actually, this is a practical work. So you're supposed to do this work. Carry out the experiments and now know what is obtainable and plot your graph and try to determine your refractive index. So let's see how we are going to go about with this. This is our rectangular glass prism. And then we draw a straight line at the middle. This straight line is what we call the normal. And then we have our light, which is now the incident ray. This incident ray, when you now draw it with your protractor, then you map out your angle. Get your angle. This angle is called the incident angle I. And then place your two pins we refer to as the optical pins on this line. And then I told you as far as ray is concerned, there must be arrowhead, because if you draw a straight line, you are drawing fine arcs. So now when you now draw this, you bring out your rectangular glass prism. And then with your protractor, you now get your angle, place it back. When you now place it back, you now come down to this place and view. At the down part of this glass, you now view these two pins. They will appear to be on a straight line. Maybe they will now appear to be on this area. So you now use your pin. Maybe this one is our first pin, 1, this is your 2, then this is the third one, and then this is the fourth one. You place your pins there. I told you it's a ray, which means we must have our arrowhead there. When this ray, like I told you, when it now hits the boundary of this particular slab, this particular ray is coming from a dense medium, which is air. It's coming from a dense medium. And it's now going to pass through a denser medium. It's either you say that it's coming from an optical dense medium and going to pass through another one that is now more optical dense medium, or you call it a denser medium. So it's going to bend. The bending now is going to be towards the normal. It's going to bend towards the normal. And then when it bends towards the normal, as we are saying, the normal is the real normal. N-O-R-M-A-L. Normal. That's what we call this line. N. And at this point, we let's say that it's O. And then when this particular ray hits this particular boundary, it will now come closer where this your line is. That's what when we say that it bends towards the normal. Mind you, it's moving straight. So there must be your arrowhead. And then when it gets to the boundary again, where this place we say it is the glass air boundary. The first one is air glass boundary. The air glass boundary. It will now hit the boundary of the glass and bend towards the normal. This particular bending is what we call the refracted ray. Let's just get it upside. This is the refracted ray. Refracted ray. Why this particular ray here is referred to as the incident ray. This is the incident ray. Then when this ray passes through this particular prism, now it gets to the boundary between the glass and the air, which we now say is glass air boundary. It will now bend away again from the normal. It will shift in the other area. It will no longer go straight. So you now place your pin. By the time you view it, you now see that they will appear to be on a straight line. After you now fix your two optical pins, which will now be P3 and P4, you remove your glass prism. When you remove it, mind you, before you do this, you will trace the shape of this glass prism on your sheet of paper. That's why I say it's a practical work. It's a technical work. You place it and trace the edges. Trace it. It will appear to be like this. Then when you now view it, after you now trace and draw your line, get your angle, you fix it back. And place your two optical pins there and view from this side. When you now view, you see that these particular two pins will appear to be on a straight line. And then you now remove it. Fix your two pins, P3 and P4. You now remove it. When you remove it, you see that it will appear in this shape. This particular ray will now bend away from the normal. And then you now, for the fact it's a ray, there must be an arrow. Mind you, as far as practical is concerned, if these two pin points are not there, please, we'll say that you are now drawing fan arcs, and that is 0 for you. So whatever you're doing is 0. And then if these arrowheads are not there, as I told you, 0 for you. So you need to be very, very careful. So if this is our A, B, C, and D as the rectangular glass prism. So we now say that at this point on time, there is another line which is your normal. It bends away from the normal. So at this point, there is an angle between the normal and this ray that's actually deviated. So this ray is what we call the emergent ray. Emergent ray. This is the emergent ray. while this angle is referred to as the emergent angle. Still, this straight line is your normal. I said it's the normal. 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 So, you should now see, or you have to see that when ray of light travels from an optical dense medium to an optical denser medium, the light ray, or the ray of the light, bends towards the normal, and when it travels from an optically denser medium to an optically dense medium, the light ray bends away from the normal. So that's exactly how refraction occurs in glass or in the rectangular glass prism. So from now, when you now have a look at, from my explanation I told you, it's a practical work. So this now is your normal, your line NO is your normal, and then your incident ray is now this particular ray that actually hits the air boundary at a point 0. The one that comes inside, we call it the incident ray. The incoming ray is the incident ray. And then when it hits the air boundary of this particular optically denser medium, the ray will now bend towards. It will now refract towards. That is what we mean by refraction. It will bend towards the normal. And then as the light passes through this optically denser medium to an optically dense medium, it's moving from optically denser medium to optically dense medium. And then the optically dense medium, a typical example is your glass or water. And then the dense medium is the air. So when light ray is moving from either glass or water, it will bend away from the what? Normal. So that is exactly what we are talking about as far as the ray of light is concerned. So I told you that this particular ray is called the incident ray. This particular ray now that bends towards the normal is what we call the refracted ray. You can also see that there is an angle between the refracted ray and this particular normal. This angle is referred to as the angle of refraction, and we denote it by R, or the refracted angle. So this is the angle of refraction. This is the angle of emergence, or the emergent angle, while this is the incident angle. So the angle inside the block between the ray and also the normal is known as the angle of refraction. So this is our angle of refraction. So we can write it here, angle of refraction. Angle of refraction. So that is this particular angle here. So we have to see that if someone actually worked on this, and then the person that worked on this is no other person than the person we know as Snell. The person known as Snell. The Snell is spelled S-N-E-L-L. S-N-E-L-L. He actually worked on this particular refraction, and then he came up with laws. And then the laws which we now see, or we now say that they are laws of refraction, that should now give us a little subheading, laws of refraction. So these laws of refraction are two. There are two basic laws of refraction, just like that of the reflection as we talked about. So this is now refraction. There are two basic laws of refraction. One, I'm stating the laws now. The incident ray, the refracted ray, and the normal at the point of incidence all lie on the same plane. I repeat. The first law of refraction says that the incident ray, the refracted ray, and the normal at the point of incidence incidence, at the point of incidence, all lie in the same plane. That is, let's go back to our drawing. He said that the incident ray, the refracted ray, and this straight line, which is the normal, all these three parameters, they lie on the same plane at this point. All of them are on the same plane as far as refraction is concerned. So, the first law of refraction says that the incident ray, the refracted ray, and the normal, at the point of incidence, at the point of incidence, at the point of incidence, all lie on the same plane. That's the three. They lie on the same plane. The second one, that is the second law, which is very, very important. You need to know this law very, very well. This law is known as the Snell's law of refraction. What did I say? This law is known as the Snell's law of refraction. Mind you, law number one is not Snell's law of refraction. It is this second law now that I'm going to give you is referred to as the Snell's law of refraction. After this man, Snell, worked on the refraction of light and came up with a tangible point and said that when you now plot the graph of the angle of incidence against the angle of refraction, that you must have a constant of proportionality, which they now refer to as, or which is now being referred to as, the refractive index of this particular glass. So this law says, that is law of refraction 2, which I told you is Snell's law. It says, the ratio of the sine of the angle of incidence to the sine of angle of refraction is a constant for a given pair of media. I repeat, the ratio of the sine of the angle of incidence to the angle of refraction is a constant for a given pair of media. So this law, he actually represented it mathematically as, he now stated this law saying that the constant n is equal to sine I all over sine R. So the ratio of the sine of the incident to the sine of the angle of refraction is a constant. That is sine I over sine I over sine R is equal to n. Where n equals constant of proportionality. Constant of proportionality, known as the refractive. It's known as the refractive index of medium 2 with respect to medium 1. So when you now plot the graph of, when you use your glass prism in performing the experiment and you plot your graph, calculating the slope, which is sine I over sine R, will give you a constant of proportionality known as the refractive index. This refractive index is the refractive index of glass with respect to air. So that is what we mean. The constant of proportionality known as the refractive index of medium 2 with respect to medium 1. So the glass is the second medium while air is the first medium. I said this law is very, very vital, is very, very important, and is known as the Snell's law. Alright. So let's have a look at the refractive index. Let's have a look at the refractive index of a medium. Refractive index. Refractive index of a medium. Refractive index of a medium. So we are saying that the constant of proportionality in this equation sine I all over sine R, we said that the constant of proportionality is n, as I told you, for a given media. That is the plural of medium. For a given media, that is air and water, or you have your air and glass. So when you plot a graph, determine your slope, the constant of proportionality there, which is known as now the refractive index. We are saying that this particular constant of proportionality, as I told you, is the refractive index of the second medium with respect to the first medium. So the question is then, what is refractive index? What is refractive index? The refractive index of a medium is a number. The refractive index of a medium is a number which gives a measure of refraction. Mind you, refraction is bending, so you can put in bracket bending. I hope you are taking these points, you are writing them down very, very well. I repeat, the refractive index of a medium is a number which gives a measure, M-E-A-S-U-R-E, which gives a measure of refraction, put in bracket, or bending of light as the light traveled from one medium to another. Let me go through it again for the last time. The refractive index of a medium is a number which gives a measure of refraction, in brackets, or bending of light as the light travels from one medium to another. That is exactly what we mean by refractive index of a glass. So what are we trying to say? If light traveled from medium 1, for example A, like the one we had in our drawing last time, if light traveled from A, which is an optically dense medium, to medium 2, e.g. glass, that is now optically denser medium. You need to know the term that I'm using there. A is optically dense medium. The glass or water is optically denser medium. So if light travels from medium 1, which may be air, to medium 2, that is the glass or water, the refractive index of medium 2 with respect to medium 1, the refractive index of medium 2 with respect to medium 1 is now given us, that is how we now write it, the refractive index of medium 1. This is how you write it. 1 will come first, then your 2. It is the refractive index of medium 2 with respect to the medium 1. So it's given as sine of angle of incidence in medium 1, sine of angle of incidence. Sine of angle of incidence in medium 1 divided by sine of angle of incidence. Sine of angle of incidence in medium 2. That will give you sine I all over sine R. The sine of angle of incidence in medium 1 divided by the sine of incidence of angle in medium 2. That is, we said that is the sine of refraction. So this is sine of refraction. Sorry, not sine of incidence again. sign of refraction. Sign of refraction in medium 2. Alright. So we are saying, but if light travel from medium 2, for instance, glass to water, like it's now coming out. So if it's coming from glass to air, or from water to air, we now say that it is now moving from medium 2 to medium 1. I hope you are putting down all these things. If light travels from medium 2, e.g. glass or water, to medium 1, e.g. air, the refractive index of 1 relative to medium 2, or with respect to medium 2, the refractive index of medium 1 relative to medium 2 will be the refractive index of medium 1 relative to medium 2 will now be 2 here, and this is 1. So this, our equation will now change to sine of angle of incidence, in medium 2 over sine of angle of refraction in medium 1. Sine of angle of incidence in medium 2 over sine of angle of refraction in medium 1. That is the refractive index of medium 1 relative to medium 2. So that's how we state it. So we now say that from the principle of reversibility of light, it is now understood that the refractive index of 2 relative to 1 is equal to the reciprocal of the refractive index of 1 relative to 2. I repeat, from the principle of reversibility of light, it's understood that the refractive index of medium 2 relative to medium 1 is the same thing as the reciprocal of refractive index of medium 1 relative to medium 2. So that is what we now see. So, having known all these things, we want to apply this to 1 or 2 mathematical problems. So let's take the first example. Example 1. The angle of incidence of light traveling from air to water. The angle of incidence of light traveling from air to water is 30 degrees. And the refractive index of air/water, the refractive index of air/water, refractive index of air/water is given as 4/3. The refractive index of air to water is 4/3. Calculate the angle of refraction. Take the question again. The angle of incidence of light traveling from air to water is 30 degrees. And the refractive index of water/air equals 4/3. The question says, calculate the angle of refraction. Calculate the angle of refraction. Alright. So we are now going to use the equation. Let's see our solution. We say that refractive index of water relative to air, refractive index of water relative to air is given as, this is your refractive index, A water is equal to sine of angle of incidence in air, sine of angle of incidence in air all over sine of angle of refraction. Sine of angle of refraction in water. That is our equation. Sine of angle of incidence in air all over sine of angle of refraction in water. We've been given that the value of the refractive index is 4/3. The value of the refractive index is 4/3. And then the angle of incidence is 30 degrees. So we now have thus sine 30 degrees, which is now the angle of incidence, all over sine r is equal to 4/3. That's the value of n, the refractive index. So when you now cross and multiply, so this implies that 4 sine r is equal to 3 sine 30 degrees. 4 sine r is equal to 3 sine 30 degrees. So this implies that r, which is the angle of refraction, is equal to 3 sine 30 degrees. It's equal to sine inverse. It's equal to sine inverse of 3 sine 30 degrees all over 4. So that will be the value. 3 sine 30 degrees all over 4. So that will now give us the sine inverse of 3 sine. This will now give you, if you divide this to give you 0.75, then sine 30 degrees will now give you 0.5, which is half. So multiply by 0.5. 3/4 will give you 0.75. And then sine 30 will give you 0.5. So when you now try as much as possible, this should now give you sine inverse of 0.3750. 0.3750. So when you now take your sine inverse, this apply that your angle of refraction will now give you 22.02, which is approximately 22 degrees. That's your answer. So that's the answer. So when we now have our incident angle to be 30 degrees, then our angle of refraction will now give you approximately 22 degrees, which the refractive index will now result to 4/3. So that's how to apply that particular area. So before we'll be able, let's talk about refractive index and wave speed. Refractive index and wave speed. How do we relate refractive index with wave speed? So that's our subheading. Refractive index and wave speed. Refractive index and wave speed, we may still say that is the velocity of wave. I hope we are taking down all those things. Very, very important. Thank you very much. Refractive, or the refraction of light, as we said, is as a result of difference in the speed of light. It's either you say in the velocity or you say in the speed. So refraction of light is due to difference in the speed of light as light travels from one medium to the other. As light travels from one medium to the other. So the difference there. So when we now say the refractive index of 1 relative to 2, 1 relative to 2 will now be the velocity of light in medium 1. That is velocity of light in medium 1 all over velocity of light in medium 2. So that's all. The same application in the other one. The velocity of light in air, assuming air is the first medium, all over the velocity of light in the second medium, maybe that of the glass. So let's take the second example using this particular equation to solve it. It says, the velocity of light in air, the velocity of light in air and glass are 3.0 times 10 raised to power 8 meter per second. The velocity of light in air and glass are 3.0 times 10 meter per second and 1.8 times 10 meter per second and 1.8 times 10 meter per second respectively. Full stop. Calculate the sine of the angle of incidence. Calculate the sine of the angle of incidence that will produce an angle of refraction of 30 degrees. That will produce an angle of refraction of 30 degrees for a ray of light. For a ray of light incident on the glass. For a ray of light incident on the glass. All right, let's quickly apply this. Let's quickly apply. So we now say that our refractive index, we've been given that the velocity of light in air, that is VA, is equal to 3.0 times 10 raised to power 8. And then we also have that our V, which is what glass, is equal to 1.8 times 10 raised to power 8. All these ones are meter per second. Meter per second. So we need to use our equation, sine R is equal to 30 degrees. So using the equation, your N, which is air to glass, is equal to V velocity in air all over velocity in glass. Velocity in air all over velocity in glass. So, this is equal to what? Sine I all over sine R. That's all. Sine I all over sine R. So, when we now see those equations and the values are being given, so what are you to do? Just quickly fix in your value. This is equal to, the velocity of air is 3.0 multiplied by 10 raised to power 8. All over 1.8 times 10 raised to power 8 is equal to sine I all over sine 30 degrees. That's all. You don't have much to do that. So you can see that this can eliminate this comfortably without stress. So what do? You cross and multiply. Then this implies that if I make my sine I the subject of formula, I will now have 3.0 sine 30 degrees all over 1.8. So that's what you have. So when you now multiply out, what you have is 1.5, because this is 0.5. If you like, this is equal to 3.0 multiplied by 0.5 all over 1.8. So that will give you 1.5 over 1.8. So when you now divide, you cannot get whatever you want. So you take the sine inverse of I. I is equal to sine inverse of 1.5 over 1.8. So when you use your calculator, it will now give you 0.83 approximately. So that will be the sine of the angle. 0.8 approximately. So if you use your calculator and calculate, it will give you 0.8 approximately. Alright? So let's just go through what we've just done so that it will now stick into our brain. Let's see what we have just done today. So in summary so far, we've been able to talk about when light, we said that when light travels from an optical dense medium to an optically denser medium, the light will bend towards the normal. And when it now travels from an optical denser medium to an optical dense medium, the light will bend away from the normal. That is when light is traveling from air to glass, it will bend towards the normal. And then when it is traveling from glass to air, it will bend away from the normal. We also establish a fact that when we now try as much as possible to see to the laws, we said that we have two laws of refraction. And the first law said that the incident ray, the refracted ray, and the normal, at the point of incidence, all lie in the same plane. That is number one. Number two, I told you, is very, very important. That is what we call the Snell's law of refraction. And the Snell's law says that the sine of angle of incidence, the ratio of the sine of angle of incidence to the sine of angle of refraction is a constant for a given pair of what? Medium. I repeat, that is very, very important. That is actually the question that WAEC is interested in. They will tell you to define Snell's law of refraction. It's not talking about law one, or don't go along defining the two laws. Just define the second law, which says the ratio of the sine of angle of incidence to the sine of angle of refraction is a constant for a given pair of what? Medium. That is the Snell's law. So we have also learned that the refractive index of a medium is a number which gives a measure of refraction or the bending of light as light traveled from one medium to the other. So before we go, take down the assignment. 1. State Snell's law of refraction. State Snell's law of refraction. 2. What do you mean by the statement? What do you mean by the statement? Quotation mark opens. The refractive index of glass is 1.65. Quotation mark closes. The refractive index of glass is 1.65. 3. The floor of a swimming pool is 50 meters deep, appears to an observer to be 30 meters. Calculate the refractive index of water in the pool. I repeat. The floor of a swimming pool, 50 meters deep, appears to an observer to be 30 meters. Calculate the refractive index of the water in the pool. And finally, the refractive index of glass with respect to air is 1.65. The refractive index of glass with respect to air is 1.65. If the speed of light in air is 3.0 times 10 raised to power minus 8, determine the speed of light in the glass. If the speed of light in the air is 3.0 times 10 raised to power 8 meter per second, determine the speed of light in the glass. Remain safe and God bless. I still remain your physics teacher, Asaga Prince Chinebompa. Bye for now.